Welcome to Lecture 4.1, Basic Matrix Algebra. The topic of this series of lectures in Section 4 is Systems of Differential Equations. We will almost entirely be focused on 2x2 systems of linear equations. Recall that we saw a short preview to this in the beginning of, I think it was Lecture 3.1, when we saw second-order ODEs for the first time, and we saw how we could convert a second-order equation into a system of two first-order equations. And we do that using matrices. So this is something that we will review, not in this lecture, because this lecture will be focused just on the matrix algebra, a review of not only how to add and subtract matrices, but how they represent systems, and just some other basic properties and some tools that we will need for the remainder of this section. Okay, so as an introduction, I think I said a lot of this. To analyze systems of differential equations, we need to heavily rely on matrix theory, which sometimes is called linear algebra. And so this is something that we'll review in this lecture. We will mostly focus on 2x2 matrices for several reasons. First of all, it's simpler, and also for 3x3 matrices, it's a lot more work, and you don't gain too much more in the theory. I think the general themes are the same. Okay, so the first thing that we want to learn is how to add, subtract, and multiply matrices. I probably should have said multiplying instead of subtracting here, but I guess this is fine. It should be clear. So before we actually do that, I want to mention that if we have an unknown matrix, for an unknown number, we often use a variable like x. If we have an unknown matrix, capital A, we often denote it like this with these indices. And so I know, I remember always getting confused as to whether the 1, 2 entry is up here or whether it's down here. And so the way I like to think of it is these entries are increased. If you think of these entries as numbers, at least the subscripts, then they are increasing as you would read a book. So from left to right, line by line. So that way you're never going to forget that 2, 1 is down here and 1, 2 is up here, because in numerical order, 11, 12, 21, 22. Okay, so adding these things up, I think you know how to do this. You just do it component by component. This is A11 plus B11, A12 plus B12, A21 plus B21, then A22 plus B22. Now multiplying matrices is a little bit trickier. What you absolutely do not want to do is multiply them component by component. That's the wrong thing. You likely learn how to multiply matrices in high school for reasons that I have simply do not understand. I think it's a completely irrelevant thing to learn at that age, because seriously, what's the point? Even if you know how to do it, you don't understand what you're doing. Maybe by now they've changed that, but at least a couple of years ago when I was teaching 208, my students told me that they learned how to multiply matrices in high school. Okay, so how do you do this? I think the best way to think of it is you do row by column. So this first entry up here is this row times this column. So think of these as a dot. It's like this is a row vector times a column vector, and you're taking the dot product. So this first entry is A11 B11 plus A12 B12. This next entry is the first row times the second column. So that's A11 B12 plus A21 B22. And then this entry down here is this row times that column. So that's A21 B11 plus A22 B21. And finally, this last entry is this row times that column, which is A21 B12 plus A22 B22. Okay, so next we have to talk about how to multiply not how to multiply, but when we can multiply matrices, we can't just multiply any two matrices in any order that we want to. But an absolute requirement is that the size of a row of the first matrix better be the size of a column of the second matrix, and that's the only requirement. So one way to summarize this is just say that so we can only multiply an n by m matrix by an m by r matrix, and the result is an n by r. And let me explain what I mean by this. So n by m means n rows and m columns. And if you don't remember whether it's rows by columns or columns by rows, here's a surefire way that I have to remember. When I hear n by m in that order, I draw an L. I say that is n this way and m this way. So that's n rows and m columns. And that way, you'll never forget it. So here's another little neat trick about how to remember what you can multiply by. I think it's best shown by an example. So let's take an example. Let's take A, B, C, D. I can't remember if I said this or not, but often it's often easier to write matrices like this with parentheses in it as with brackets. This means exactly the same thing, whether I use a bracket or a parentheses. It's just for ease of notation. So this is a, well, let's do this. So these are two matrices that we can multiply, and this first one here, doing the L trick, is 2. Well, that's, you don't need to. It's 2 by 2, and this is 2 by 1. So this is 2 by 2, and this is 2 by 1. And the result is, so here's what I do. I say these are things I can multiply by because those numbers are the same, and the result is the two numbers that I did not circle, a 2 by 1. So let's multiply these. So it's these rows by this column. So the result of this is AX plus BY on top and CX plus DY on the bottom. And again, this is a 2 by 1 matrix. So this is 2 by 1. And again, that's this 2 and that 2. So another example, let's do one more. Let's do, say we have A, B, C, D, E, F times X, Y, Z. This is, so this is 2 by 3 and 3 by 1. So I didn't leave enough room. Oh well, 2, this is, come on, 3 by 1, and this is 2 by 3. We can multiply these because those things are the same. And the result is a 2 by 1. So it doesn't hurt to draw these rows. So the result of this is AX plus BY plus CZ on top, and DX plus EY plus FZ on the bottom, and this, of course, is 2 by 1. So these are examples. Let's also helps to see a few non-examples. So these are non-examples, meaning that they do not work. So we cannot multiply A, B, C, D times 1, 2, 3, 4, 5, 6. Because this is 2 by 2, this is 3 by 2, and these things are not equal, so that does not work. Another example of something that does not work is if we try to do x, y times a, b, c, d. That does not work either. So we can multiply these two in this order, but not in the other order. And let me give one more definition at the end of this slide. Actually, I didn't save myself room to do it, so why don't I do it up top? Let me switch to my pen first. This is a definition I will use all the time, so remember this one. An n by 1 matrix is called a vector. So remember that. Anytime we have a matrix like this, or like this, or like this, it's also a matrix, but we call it a vector. And we'll understand this more as we see more examples and more applications. Okay, so I want to do an application of matrices. This is probably the most fundamental, and it's usually the first one that students see. And it's how to write a system of linear equations in matrix form. And I gave a brief preview about this, I think, in lecture 3.1, although I didn't really explain what I was doing, and I said, wait till later. And this is now later. So here's a system of two equations and two unknowns. So I should say that x1 and x2 are the unknowns. And instead of using actual numbers, like digits, I'm using indices of the matrix. So each aij entry and b1 and b2, these are supposed to be just numbers. So this is something we can write in matrix form, like this. So this is called matrix form. So matrix form. A11, A12, A21, and A22 times x1, x2 equals b1, b2. So we often write this as A, x equals b. We don't always have to put the hat and the x's and b's. Often we do that just to make it clear that is in fact, again, this is a vector and that's a vector, though often it's clear from the context. And usually when it's typeset, we type these as bold. So, okay, so why does this equal that? Well, let's actually see. Let's multiply this guy out using our matrix multiplication, and look. And if we do that, we actually get a vector that looks like A11 x1 plus A12 x2, and then A21 x1 plus A22 x2, and that is equal to b1 b2. And notice this equality. This is exactly the same thing as how we write it up here. So solving this is akin to solving this. So the goal is to solve for x. And so you know how to do this. This is like middle school or high school algebra. Like that will still work here, but there's actually a lot better ways and quicker ways to do it for general systems of equations that don't involve eliminating variables one by one. Okay, so here are 3 examples of systems, things that you probably learned how to solve in junior high. Let's go over how to do these quickly. I know it's something you know, but I just want to review what sort of things you can get from a system. So this first one, if I were to ask you to solve, you would probably say x2 equals 3x1 minus 8, and then you would plug that thing into the second equation, and you would say x1 plus 2 times 3x1 minus 8 equals 5. And then it's not hard to see that x1 equals 3 and x2 2 equals 1. So graphically, if you were to plot solution something like this, then you have one equation which is 3x1, not necessarily to scale, not to 2, I should say, to x2. x2 equals 8. Then you have the other equation, which is something like this. This is x1 plus 2. x2 equals 5. And I should probably say that this is the x one direction, this is the x2. And of course, this point of intersection is 3, 1. So generally, if you have a system of two equations and two unknowns, assuming the lines are not parallel, you're going to have one and only one solution. So this second equation, if you were to do the same thing, then you would probably solve for x1 in one of these things, this first one, and plug it back in. Let's try this. So you would say x1 equals, say, 1 minus 2x2. And if you plug that back into the second equation, then you get 1 minus 2x2 plus 2x2 equals 5. And that should be equals 5. And of course these things cancel, and you get that 1 equals 5. And that's impossible. If you were to plot this, what you get is these two lines are actually, this is x1 again, and this is x2. And these two lines are actually going to be parallel. So this is x1 plus 2x2 equals 5, and this is x1 plus x2 equals 1. And finally, the last one, you probably guess what is coming, is, you can probably see it, is this is a scalar multiple of that equation. So if you were to solve the system, you would probably actually solve for the x1 on the bottom first. You would probably say that x1 equals 5 minus 2x2, and plug this back into here, and you would get 2 times 5 minus 2x2 plus 4x2 equals 10. So if you do this, you notice that this is going to give us a negative 4x2 and a positive 4x2, so these things are going to cancel, and you're going to get that 10 equals 10. So that means any values of x1 and x2 are going to give you this equality. So this is always going to be satisfied. And if you were to plot this one, you get both of these equations. This is 2x1 plus 4x2 equals 10, and it's also x1 plus 2x2 equals 5. So these are the three cases when you have a system of two equations. You either have a unique solution, no solution, or infinitely many solutions. So here you have a unique solution, no solution, and infinitely many solutions. And we'll soon see how to figure out which one of these cases we have just based on the actual matrix. Okay, so here's the general case. And now let's suppose we have just indices instead of numbers, so we can easier to tell things apart. So let's solve for x1. I'm not going to actually do this, but it's easy. You know how to do this. You get a22 b1 minus a12 b2. So it's just basic arithmetic, basic algebra. a11 a22 minus a12 a21, and then x2 is a11 b2 minus a21 b1 over a11 a22 minus a12 a21. So I want you to notice something. So of course this is going to work assuming this denominator is non-zero. Otherwise you can't divide by this. So let me circle this. So this thing better be non-zero if you want to be able to solve for x1 and x2 like this. So let's write that out. Note there will be a unique solution, namely the solution I just wrote above for x1 and x2 if and only if, so that means this is a necessary and sufficient condition, a11, a22 minus, make sure that looks like a 2, minus a12, a21 is not equal to 0. So this quantity, let's write a definition. This quantity is called the determinant of A, of this matrix, A11, A12, A21, and A22. And it's denoted det of A. And sometimes, if we want to write that, it's nice to write, if we write absolute value symbols, A11. So anytime we write a matrix with absolute value symbols, sometimes it's just convenient to do this. Here we actually mean determinant. So this means determinant of A. So this, of course, has a geometric interpretation. I don't know if I want to have a space down here. I wrote kind of big above, but so let me write it above. So geometrically, so let me sketch this. I'll let you verify this on your own, but so these two equations, this is just basic algebra. So if this is x1, this is x2, and then this first equation, say this is let's say that this is row 1, and I'm going to say that this is row 2. Or maybe I probably should have called it equation 1 and equation 2. I mean, so this is equation 1 and this is equation 2. So the slope of equation 1, it's easy to see, is negative a11 over a12, and the slope of equation 2 is negative a21 over a22. So if the slopes are different, then there will be a unique solution. So if the slopes negative a11 over a12 is different than negative a21 over a22, then there will be a unique solution. Then there will be a unique solution, and the fact that this is different means that this cross product, this times this, or let's just write it down, and a11, a22 minus a12, a21 is going to be, which is the determinant, is going to be non-zero. So a necessary and sufficient condition for the slopes, so let's say it this way, the slopes being different is equivalent, well, it is exactly this condition, and that is equivalent, just by cross multiplication, to the determinant being non-zero. So to summarize, there is a unique solution if and only if the determinant is non-zero. So let me write that. Summary. There's a unique solution if and only if, that's short for if and only if, the double F, the determinant of A is non-zero. Okay, so the next concept, which is important and we need to introduce, is that of the identity matrix. So the 2 by 2 identity matrix is this. I like this font. I just don't like how they do capital I's. So that is a capital I. It's this for. Let me show you the pattern. So the 3 by 3 identity matrix is going to be this, and I think you can see the pattern for n by n. So we call this the main diagonal of the matrix. So 1's down the main diagonal and 0's elsewhere. So why is this called the identity matrix? So note, simple observation, take any matrix, any 2 by 2, A, B, C, D, and multiply by the identity, 1, 0, 0, 1, and look what we get. Notice we get A, B, C, D. Check for yourself. And similarly, this is also what we get if we multiply in the opposite order, 1, 0, 0, 1, something like this. So this is the matrix analog of the multiplicative identity, which is 1. So let me write that down. This is the matrix analog of the multiplicative identity 1. And so by this I mean for any number, take any number, real number, what do I want to call it? K times 1 equals K, which is, make sure that's an actual 1, which is the same thing as 1 times K. So 1 is a number that has the property that anything you multiply it, you get back itself. The identity matrix has the property that any square matrix of the same size that you multiply it on either side, you get back itself. So next, we want to look for a matrix analog of inverses. So say next goal, find a matrix analog of inverses. And what I mean by this is if you take any fraction, A over B, so I'm assuming B is non-zero, then there is another fraction. So I'm assuming, so let's just assume that both of these are non-zero. So for any fraction, there is another fraction, B over A, so A over B times B over A, which equals the identity. So this is called the inverse, the multiplicative inverse of this number. And this thing that we got back, this is the multiplicative identity. So what we would like is, given a matrix, is there something we can multiply that by? Is there an inverse of that matrix that when we multiply it back, we get the identity? So in other words, differently, so given A, we want a matrix B such that A times B equals, and B times A are both the identity. So such a matrix B is called the inverse of A, and is denoted A inverse, or A to the minus 1. So notice that not every matrix is going to have an inverse. Like the 0 matrix is not going to have an inverse. Well, then again, the 0 number does not have an inverse either. 0 times, there's nothing you can multiply 0 back to get back to 1. But it's more complicated than that with matrices. It's not hard to see that if you start with this matrix, there is nothing you can multiply it by to get back the identity. 0, 0. It just doesn't work. So that's never going to be the case. So there are non-zero matrices that do not have inverses. And we will soon see and understand which matrices do have inverses. So I think the best way to show you what the inverse of a 2 by 2 matrix is just by example. So notice that, let's take a 2 by 2 matrix, A11. Let me just write this one out. Two down there. And notice that if I multiply this matrix times the following matrix, so here I'm going to swap the order of these two things, and I'm going to put negative signs on these two. So this is A22, A11, and I'm going to put negative signs in front of, I'm not going to swap the order of the other two entries, I'm just going to make them negative. Notice that if you multiply these two matrices together, look what you get. So here, remember we're multiplying this way. So this first entry is A11, A1, A22, and then times A21. We get the same entry down here. And these things are both 0. Okay, and this is just the determinant of A times I. So given if this matrix, let's call this matrix A, then A times this matrix here, let me actually put a little line here to separate this. So A times this matrix is a scalar multiple of the identity. Okay. So in other words, we can divide, so take this equation and divide through by this number, and then what we get is A times this matrix divided by the determinant is exactly equal to the identity. So this is a formula for the identity, or sorry, for the inverse of A, is take A, swap these two entries, and put negative signs here, and then divide by the determinant. To summarize, the inverse of a 2 by 2 matrix, now let's just call it A, B, C, D, when it exists, is the following matrix. So this is 1 over the determinant of A times this matrix right here. And when this exists, so notice this exists precisely when this is non-zero. So this thing better be non-zero. So when the determinant is non-zero, It's equivalent to saying when A inverse exists, we say A is invertible or it's non-singular. I prefer to use the word invertible. I think it's weird to have a positive thing, the inverse existing, having an adjective with a non in front of it. Otherwise, A is non-invertible or singular. So notice that, well, let's say several things. First of all, I think I've already said this, but let's write it down. A is invertible. I'll often abbreviate that as like this, invertible if and only if the determinant of A is non-zero. So back to systems, that's actually the title of this slide. Let's take a 2 by 2 system, or just a general n by n system. This is going to hold more generally, as you'll see. So let's suppose that we want to solve ax equals b for x. Then all we need to do is just multiply both sides of the equation on the left by A inverse. So if A is invertible, then write A inverse times AX equals A inverse times B. Notice this right-hand side, or sorry, this left-hand side, that is equal to the identity. So this is equal to the identity matrix. This is I times X, which is just X. In other words, this tells us that the unique solution is A inverse B. Notice that we had to be careful to write this, or to multiply both of these on the left, not the right. Generally, we can't necessarily multiply this matrix on the right-hand side of this equation. And notice that this is the analog of solving algebra equations. If I were to give you, say, 5 times x equals 10, what would you do? You divide through by 5. Really what you're doing is you're multiplying by the multiplicative inverse of 5. You're saying, well, 1/5. Actually, let me actually write that a little different. Let me say you're multiplying by 5 inverse, or 5 to the negative first, or 1/5 times 5 times x times 1/5 times 10. And of course, this is equal to 2. And over here, because that's equal to 1, this is equal to x. So this is really the analog of what you learn how to do in your basic algebra class. So let's do an example now. Let's return to that example we saw before. So let's solve 3x1 minus x2 equals 8, and x1 plus 2 equals 5. If we write this in matrix form, that's just 3, -1, 1, 2. This matrix times this vector. 8, 5. So the determinant of this matrix, remember, is this product minus that product. So I'm going to call this A, I'm going to call this X, and I'm going to call this equal to B. And notice that the determinant of A equals 3 times 2 minus 1 times -1, and that's equal to 7. So A inverse is 1 over 7, 1 over the determinant, times the matrix that we get when we swap these two entries. So let's put a 2 there and a 3 there and make these two negative. So let's make that a positive 1 and a negative 1. Now, you're welcome to pull this 1/7 inside the matrix, or you can leave it out. It doesn't matter. So that means that the solution to this, now remember the solution was 3, 1. Well, it's x, which is just x1, x2. So it's A inverse times B, so that's 1/7 times 2, 1, negative 1, 3, times 8, 5. So this matrix product, so this row times that column is 16 plus 5. That's 20. Well, I'm going to keep the 1/7 out here. 1/7 times, that's 21. And this row times this column, this is negative 8 plus 15. That's 7. And so this is 3, 1. And that's exactly what we got before. In other words, this is saying, so this is A inverse times B. And this is, of course, x. So this is just saying that x1 equals 3 and x2 equals 1. You may say this is not necessarily easier than just plugging in and solving it, but it's certainly something you can plug into a computer, use things like Wolfram Alpha 4, and it's going to be actually much easier when we have larger matrices, things like 3x3, 4x4s, which we won't do in this class, but it's certainly a very nice tool to have. Many math classes are filled with derivations and proofs of results. And the purpose of this is to supposedly give the student the intuition as to what's really going on. But it's been my experience, both as a student and an educator, that this usually doesn't have the desired result. Usually the proofs are complicated, the students don't follow them, and not much is gained from the process. So what I like to do instead is I like to present an alternative way to think about things. I'm not deriving anything or proving anything. I just want to give you a different perspective, different viewpoint, which will help you understand the material better. It just gives you a different way to think about things. And this is a way that I really like. It helps me understand matrices. And maybe it won't help you right away, but maybe you see it now and you keep it in mind as we go throughout the class. It may be something that you want to come back to. So a 2x2 matrix, I claim, is a linear map from R2 to R2. So what does this mean? So R2, I mean like the xy plane. Alternatively, the set of all vectors, two-dimensional vectors. Basically the set of all these guys. And by map, I just mean function. So you're used to maps that are from R to R. So like F goes from R to R, might be something like f of x equals x squared. Or in vector calculus, you saw something like g as being a function from R2 to R2 to R, something like g of x, y equals maybe x plus y. Or in our notation of writing vectors as columns, that might be, we might write this as g takes x, y, and it maps it to x plus y. So here we input a number and output a number. Here we input a vector and output a number. And here we are inputting a vector and outputting a vector. So explicitly, what I mean by this is, so here's A. And we input, so x1, this is our input vector, and our output vector is this. It's just the product of these. So this is the input vector. And this is the output vector. also in R2. So think of this again as like some black box. You input this, and you output, and that thing spits out. So here's a way to visualize this. And here's a visualization I really like. I sort of made this up, but just because it helps me understand what's going on. So let me draw two vectors. Something you'll learn more about if you take a class in linear algebra. I think at Clemson that's 311. Or now it's 3110. I hate having that extra digit. Okay, so I'm going to draw. This vector is I'm going to call it E1. That's a standard name for it, which is the vector 1, 0. And this vector up here is E2, which is 0, 1. So these two vectors, well, that's not a perfect drawing, but so these two vectors determine a grid, a square grid of unit length and so you can think of like points as, so the point 2, 3 is 1, 2 over and 3 up. And of course this is x1 and this is x2. So think of this as my input vectors. My input, my x's. And now if you apply A, what I want you to picture, I'm going to draw it over here, but picture this being overlaid. So imagine you were to pick up E1, like pick up the tip of this arrow and put it anywhere you want to. Let's put it up there. So move this vector to being up here, and let's suppose that this line came along with it, and all of the parallel lines came along with it as well. So in other words, what I'm going to try to draw, I don't know if I can do this well, is let's suppose that you picked up that vector and you moved it to there, something like that, right there. So in that case, I want to say that this. Oh, and let me do the other one. I think I'll be able to draw better if I. So let's pick this guy up and let's move it to, say, up there. So this gets moved up to here, and the axis goes along with it, and all of the vertical lines become parallel. So in other words, this is going to be my A times E1, right, where E1 gets sent to via this function. And let's declare that this vector, I'm just doing an example, that this vector is A times E2. So as we move up these vectors, the grids go along for the ride. So I have something like this. Can you picture that? So again, I can pick up with my two fingers these things and move them, and the grids go along for the ride. And what I get is something like this. Okay, so that's really what's going on. Let's take a. Let me finish this grid like this. Yeah, I'm going to extend this. Okay, so let me pick a vector up here. How about this is 2, 3, right? So this is V equals 2, 3. And so when I apply A, this vector 2, 3 gets mapped to 2 steps in this direction and 3 steps in that direction. So it actually gets mapped. So this is AV. And you can actually, or when I say this is AV, to figure out what this vector is, how many x's and how many steps in the x and the y direction, literally just take this matrix and multiply by the vector 2, 3, and that'll tell you what this length is and what that length is. Okay, so what else do I want to say about this? So note, that if I take A11, let me take this matrix, and let me multiply by 1, 0. In other words, let's see where that sends this guy. If I do that, I just get A11, A21. In other words, this vector here, you can figure out exactly where it gets sent just by, it's this vector right here. So over here, so in this case, this vector, let's just suppose this is, it looks like it's maybe, what does that look like? Maybe it's like 1.5, and looks like it's 1.5 and let's say 0.75. That's about right. And also notice that this matrix, or this should be 1, 1. If I multiply this by 0, 1, notice what I get. I get the second column. So in other words, that's just this column here. So you can read off where this vector gets sent just by that column. So in this case, this column, this vector looks like it's about, I'll say 1, 2. So does that look about right? Maybe 1, 2. So if that's the case, then this matrix A really was 1.5, 0.75, 1, 2. This matrix right here. Okay, so the last thing I want to say about this is if I want to undo this map A, then I can just pick up these two vectors, AE1 and AE2, and just move them right back. And that is, in fact, the inverse that we learned about. So applying A inverse actually takes, so applying A, think of it as the mapping, the function that takes this grid and sends it to this grid, and A inverse is the function that does this in reverse. So, one thing, this is usually not taught in an undergraduate, so here's a fact that is, I don't want to say usually, I'll say frequently not taught even in the undergraduate course on matrices. Let me take, so obviously this box here has area 1, right? This is the unit square, area equals 1. So you can ask, what is the area of this parallelogram? And it turns out that the area of that area is actually the determinant of the matrix. Remember we just learned about the determinant? That actually has a geometric meaning. Think of the determinant as the scaling factor. So the determinant literally tells you how much a unit square gets blown up, what factor it gets blown up by. Now I should say absolute value because you can't have negative area, but you could have negative determinant. And technically, if the determinant's negative, that means that there was also a reflection involved. In other words, that this vector is on the other side of that. But that's a detail I don't need to worry about. So let me ask you this. When can you, there is not always an inverse to A. There is sometimes. And remember that there's an inverse precisely when the determinant is non-zero. So I can ask, and here's a visual proof of that. When can I undo this picture? Well, any time that I actually have a parallelogram that's truly two-dimensional, I can just take these vectors on the side and I can just move them right back to there, back to there. However, if the area of this parallelogram is 0, meaning, so here's how that could happen. So let's suppose you have maybe E1 gets mapped, let's do it like this. Let's suppose these two vectors get mapped to this one and that one. Now my grid is no longer two-dimensional, it's only one-dimensional, and the area, this parallelogram now has area 0, so the area equals 0, which is the determinant of A. In this case, well, I should say the determinant of A and then absolute value sign. In this case, I can't pull apart these two vectors
and go backwards. So this is a visual proof that a matrix is invertible. It has an inverse if and only if this determinant is non-zero. Okay, so the last thing I want to do before ending this lecture, I guess I'm going to keep this up though it's not relevant to this, is I want to bring back the word homogeneous. So if I have a system, if I have a system like, that should be A11, let's make that a little better, A11. So suppose you have a system like this. A system like this, and B1 and B2 are 0. The system is homogeneous. Homogeneous. I think you can read that. Homogeneous. So really, in matrix notation, this just means A times X equals 0. So graphically, that means that if you plot these two lines, what you have is you have two lines that actually go through the origin. And so that means that the zero vector is a solution. These lines will intersect the origin, and you can see that right away. A times the zero vector equals 0. So one note, this may seem trivial, but it's worth mentioning because it will come up, is if the determinant of A is non-zero, then this is the only solution. Because remember, if the determinant is 0, then these two lines are the same. And so we have two parallel lines that go through the origin, and there's infinitely many solutions. But if this is non-zero, these lines have different slopes. So here's the graphical reason as to why this is, but it's clear. And algebraically, so I always like tying the algebra to the graphical picture. So if AX equals 0, you just multiply both sides by A inverse 0, and this cancels to give you the identity matrix, and that tells us that X equals 0. So I mention this because homogeneous systems are going to correspond to homogeneous systems of algebraic equations are going to correspond to homogeneous systems of differential equations.